Hi guys, welcome back to Data Every Day. Today we're looking at a dataset of human activity recognition with smartphones. So recordings of 30 study participants performing activities of daily living. And so there's 6 different labels: walking, walking upstairs, walking downstairs, sitting, standing, laying. And basically, based on information collected by the smartphone on their waist, we're going to try to, you can see we have 563 features here. We're going to try to predict all the way at the bottom the activity of a subject, which is one of these 6 values right here. Alright, so let's get into it. Let's just write title of the notebook, Human Activity Recognition. Alright, so I have, we're going to use TensorFlow to train our model today. And I'm not doing feature selection. I tried filtering some features because we have so many, but I found there was a decrease in performance even if I took away just a few. So we're going to keep all 563 features in our dataset. So we're using NumPy and Pandas just to deal with the data, Matplotlib maybe to graph some charts at the end for the training loss, and then label encoder and min-max scaler. This can be replaced with standard scaler. I mean, it doesn't matter too much. I haven't tried it with standard, but we'll see how it goes. Maybe I'll do both. We'll try them with both, and then we'll import TensorFlow. Alright, so before we start, this is something I want to start doing is seeding TensorFlow. So tf.random.setSeed, and this is a random number that will ensure that all of the our results, like the random initialization of weights in the model, will always be the same for each run of the notebook. So this is the one I use. It's just a random number. It chose 4445444. So we'll seed it. And you can also seed NumPy, but we're not doing any NumPy randomization, random generation today, so we don't have to. Train df. Yeah, so we have a train and test set as separate files. So let's load it in with pandas.readcsv. And we'll do the same thing, but for test. We'll just replace that with test. And this will be testdf. Okay, let's get some info on each of them. Alright, so we have... oh wow, okay, yeah, this is great. So, let me just look at it. So you see there's, it already seems to be scaled, probably with a standard scaler. However, at the end, the subject number, I wonder if we should keep subject number in. No, well, we'll keep it, it's fine. But you can see that the subject number is actually an integer, but everything else seems to have been scaled with a standard scaler. So they're all floats with probability of mean 0. We can check the means of each column by doing data.columns. Okay, data.mean. Can you do this? Oh, it should be train df. Oh yeah, you can get the mean for each column this way. And they all look to be around 0. So yeah, I'm not sure exactly what method was used to scale them, but I think we'll scale them again just to be sure. Alright, so let's check one more thing. I want to see if there's any missing values. So train set missing values. And we can do train df.isNA.sum to get the total number of missing values in the dataset. And 0. So no missing values in the train set. Let's try it with the test set. Test df.info first. The reason I'm doing info is you can see we can be sure that there's actually 561 floats, 1 integer and 1 object, and the integer and object columns are these ones at the end, integer object. So we know that we don't have to worry about any like categorical variables hiding in there. And let's check the test set missing values. So test df. Also 0. Okay. So we're good to start with this. So let's start splitting the data. I keep writing data, it should be train df. So we're just going to split off the activity column from the rest of the data. And so we're not going to use train test split today because we have already split into train and test. So yTrain will be train df sub activity. And let's make a copy of it. Alright, and x will be, or xtrain will be train df dot drop activity from x is 1. And we'll make a copy as well. Then we'll just copy that and do the same thing for the test set. So grab these and grab these, and we're good to go. Alright, now let's encode the labels. So yTrain currently looks like this. It's a bunch of different of these 6 labels that we saw earlier. Let's just get the unique values so we can see. And yeah, we can get the value counts actually. It's a pretty even class distribution. I mean, it's a little skewed on from the max to the min, but they're most of them are around 1200. So not too bad. We could still probably compute some class weights if we wanted. Perhaps I will, but in any case, we want to well, why don't we num classes equals 6? Just have that variable. But we want to label encode this. So normally I will just do a dictionary mapping that will map a text label to an integer number, but because we have 2 different data sets that we're applying the same mapping to, I just want to use sklearn's label encoder, because we can fit it to the train set and apply the same fit to both the train and the test set, so that we know that the labels are matching up in both sets. So let's fit the label encoder on yTrain, sorry. And then we're going to transform both yTrain and yTest via the same transform function. So label encoder dot transform y, and then here is going to be train, here will be test. So we're transforming train and test based on the fit that we applied just with train. Okay. Now let's scale the data. Like I said, it's already been scaled, but we're just going to scale it again, just to ensure that it is as scaled as it can be. So we can use a standard scaler. I want to try it with both the min-max scaler and the standard scaler. So first I'll try standard. I'll just comment this one out. And then xtrain, we're going to scale xtrain and xtest. We're going to do the same thing. We want to fit it on scalar.fit on xtrain, and then we're going to transform both xtrain and xtest based on the fit we have for the train set. So xtrain equals scalar.transform xtrain, and we'll do the same thing for test. Grab that and that. Alright. And now let's build our model. Alright, so we're going to do a standard 2 hidden layer neural network. So start off with a Keras input layer. The shape is going to be xtrain xtrain.shape sub 1. So actually I'm going to make it a vector with that length. And the reason I'm not hard coding it here is because we want to be, if we wanted to try it with fewer features or apply some sort of feature selection method, we would not have to change the line. So now we're going to create 2 dense layers, both with 64 activations and ReLU activation function. Pass in inputs here, and then to the second one we'll pass in x. Then for our output layer, this will just be another dense layer with num classes activations, which is actually 6, and a softmax activation function. And that will give us 6 different probability values, one for each class, and the class with the highest probability estimate is going to be the classification. Then we'll construct our model, tf.keras.model, pass in inputs and outputs. And then why don't we just get a summary of the model. So you can see a vector of 562 features comes in, gets fed into the 64 unit dense layer, then it's another 64 unit dense layer, and finally a 6 unit dense layer with our predictions. And you can see the number of parameters goes down each time, converging to a final 6. Alright, now let's compile our model. So we're going to use Atom Optimizer. For loss, we'll use sparse categorical cross entropy. And for metrics, we'll use accuracy. We'll store our model's fit history in history, and we'll train it on xtrain, ytrain. Let's include validation data, validation split of 20%. Batch size, how about I'll make 2 variables appear. Whoops. So we'll have batch size 32 and number of epochs. I was messing around with it. I found the best results after around 25 epochs, but I'm going to use a model checkpoint callback today, so it doesn't matter too much. So batch size equals batch size, epochs equals epochs, and then I'm going to include this callback function, actually 2 callback functions. First we're going to use model checkpoint. So model checkpoint will just save it will save the weights of the model after each run. So we're going to save it as model.h5, that's HDF5 format, and we're also going to enable save best only. So I only want to save the weights from the best epoch. So if a better epoch comes along, it'll overwrite. So at the end we'll just have one file that contains the weights from the best epoch. And then I'm also going to include the reduce learning rate on plateau callback. Reduce LR on plateau. And we're going to pass in a few arguments here. Normally it monitors the validation loss, but I found that it's doing better if we monitor the validation accuracy. Actually, I think it's called acc. Wait, is it? It shouldn't matter. I think accuracy though. And then a factor by which to scale the learning rate. 0.1 is good, so it will divide the learning rate by 10 when we, after a certain number of epochs passes, which we now specify, and I'm going to do 1. And these parameters were taken from looking around Kaggle, finding some things that worked for other people. Seems like this helping it converge with the reduced learning rate on plateau callback seems to work in this situation. Alright, so let's go ahead and train. And it's a quick train, even though we have 563 features, it's not actually that bad. But let's get the results. So first let's plot the results in a matplotlib. Not the results exactly, but the training loss over time, training and validation loss over time. So how about 16 by 10? And then okay, so let's make some axis data. For our x-axis, we want to plot the epochs. So I'm going to make epochs range be a range of the number of epochs. So that'll index from 0 to epochs minus 1. And then on our y-axis, we're going to have 2 values. We're going to have train loss, which will be history.history sub loss. So history is what we saved the model's fit in, and it has its own attribute called history. If we take a look at it, it has each metric or loss, and then a bunch of values for each epoch. So I'm getting just the training loss from it, and we're going to plot that along the y. And then val loss will be the same idea. Whoops! Oh my god, it's meant to be holding control, except val loss instead of training loss. All right, and then we can plot the data. So we're going to plot on the x-axis epochs range, and on the y-axis train loss. And let's label it training loss. Then on the same plot, I'm going to plot another value, which will be the val loss. Okay, then we can enable the legend, give it a title. Whoops, spoilers. Loss over time, and plt.show. Alright, and yeah, it looks like very slowly this looks to be converging, but it seems to have reached a sort of minimum even after just a few epochs. Yeah, alright, so let's evaluate the model. Actually, before we run on the test set, I'm going to load the weights from the best epoch. So over here in the output folder, you can see model.h5 was saved, and that's going to be model checkpoint saved for the best epoch. So we can do model.loadWeights, and we'll get model.h5. Before I run that, let's actually just see if we see an improvement. So we're going to evaluate on x test, y test, and we get a 92% accuracy. Now I'm going to load the weights for the best epoch and re-evaluate, and I think settle slightly higher, maybe, perhaps. Alright, so okay, the last thing I wanted to do was going to be trying with a min-max scaler instead of a standard scaler. So we're going to comment that out, uncomment min-max scaler, and then run the whole notebook again. Note that because we seeded TensorFlow at the beginning, any random generation that happens will be the same as it was the first time. So if we see a performance increase from this, we'll know it's real. And look, it actually seems to be converging much nicer. But no, we got a lower accuracy. Interesting. Maybe one more thing we could try is, instead of monitoring val accuracy, we could try monitoring val loss and running that. It seems to converge. Interesting. Because when I was doing it earlier, we got a little higher accuracy with the same seed. But it looks like we're getting around 92%, 93% maybe. And it doesn't look like the scaler helped too much. Maybe it actually, I don't know, I guess I'll probably keep it with the min-max. But yeah, that'll conclude today's video. Thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and leave any comments you have in the section below. I'll see you guys tomorrow. Have a fantastic day.